Welcome to the program. This is the Ecomodernist channel live. I'm Carl Pauls. I'm here with Gabe Ignetti and our special guest. Mark Havens is former lead researcher, a computer lab manager, and university lecturer at the University of Texas at Arlington. Formerly, he's a senior technical architect at AT&T and a former senior systems engineer at Verizon. We're going to be speaking with Mark about quantum computing on the moon. Welcome to the show, Mark.
Quantum computing on the moon. Okay, let's figure this out. As I remember last time we talked about this, when I reviewed the video footage, you made a mention about something that was contradictory to something I mentioned, I think, and I wasn't like a huge fan of building something in space that was quantum, not because not because of the its ability to maintain cooling, but because of radiation. I think was my issue. Was you can build all sorts of complexes underground with Earth as the main insulator um, for radiation protection, but you have to build all that infrastructure out in space, or maybe. But if you're talking about on the moon, that kind of changes the equation a little bit, because you can build all that infrastructure under the moon. It just becomes uh, probably a little bit more complicated. What do you call it, time wise? I mean, because you actually have to travel to the moon and land there and all that stuff. It kind of multiplies the amount of cost, but that's about it.
Mhm. So to give sort of an overview, quantum computing generally deals with observations of paired quantum states and their interactions and computations based on transforms of those states. In order to get a system in that state, we have to be at a very, very low temperature. It's like around 459 degrees Fahrenheit, below zero. Uh, and then you also have to, as you say, you have to be very aware of external energetic effects, external radiation, gammas, cosmic rays, etc., and the Earth's atmosphere, the Earth's Van Allen belts, and even the physical matter that we can put in the way of such an installation will improve its resilience by decreasing the amount of interference. So um, is there sort of a balance of those things when we talk about doing quantum computing in space? Is it better in terms of energy availability and ideal conditions on the moon rather than in near Earth orbit? What are the all of the what are all the considerations that we have to bring to bear?
Yeah, but by the way, Carl, not to interrupt, but I just looked it up. The lowest temperature at the poles on the moon is 410 degrees Fahrenheit, below zero.
Yeah, warmer than absolute zero, but much colder than the Earth.
Yeah,
Well,
yeah.
well temperature is kind of an important factor, but like I said, all the cosmic radiation and any radiation at all is it collapses the wave function, right? So you can't have any of that stuff. And as soon as you have one aspect collapsing the wave function of any of the atoms that's associated with the decoupled uh, atoms that's part of the computer, um, it basically ends the algorithm that whatever you're running. So it's a matter of making sure that that doesn't happen for as long as possible, and the longer it can go without being decoupled, without being decohered, um, the longer algorithm can run. So the more powerful your computer can be. So it's not that you won't have a completely defunctional machine. You just will have a far less useful machine if you can increase um, the probability of it not collapsing, the wave function. So you do that by lowering the temperature, and you do that by isolating it from the rest of the universe so that it doesn't collapse. And in any little particle from I'm talking about cosmic radiation from supernovas from thousands of light years away could that penetrates like gamma rays and stuff that penetrates uh, the atmosphere and even the earth and sometimes even lead, right? Can collapse that wave function, and that's what mysteriously ends the computation process. So building the infrastructure outside of the Earth requires a lot more engineering, right? So and I'm by a lot, I mean a lot. Like it's like you'd have to really put a lot of material out in space in order to seal it so that it can work at all, because it's going to be bombarded, right?
I
Does that
see
make
Gabe.
sense?
Yeah. And I see Gabe has a question.
Yeah, yeah, and let me make a comment on the amount of material. Uh, the Star Tram. I don't know if you're familiar with that, which is maglev used in a near vacuum, going up mountain and going in a tube up a mountain and just using electricity to fire ships. It was all theoretical. The China's going to build it. It's going to be there in 2 years, and they could, you could the ability. I think it's a 40% reduction in the amount of was it fuel that you need, as well as you could do a lot more moonshots, probably a lot more cheaply. So you could move a lot of material. Um, Let me ask you this question. Would low gravity on the moon be advantageous or disadvantageous to quantum computing?
I don't think gravity collapses the wave function, so it probably doesn't matter.
Okay.
So it's and we know that just by. I don't know if we know that, but I don't believe that's true.
Mhm.
Simply because of how gravity works and how we're able to observe like dark matter's effects with gravity and how I've got my own paper on dark matter, and that's related to this in the sense that I believe dark matter is similar in how quantum computing works, because it's in my approach to understanding dark matter, it's decoherent matter from the beginnings of the universe that never uh, collapsed into matter. Right? It's unwitnessed matter, basically. It's matter that uh, hasn't been witnessed by other particles. That hasn't tangled with other particles.
Mhm.
So, but it still has the same gravitational impact as information. But um, but like I said, the gravitational effect shouldn't have that aspect
It,
effect at all. It's
yeah.
it's all about it's all about how it decouples with the rest of the universe, and you can manufacture that state in matter just by isolating it, right? And making sure that it's cold, and making sure that it's doesn't have any type of energy interaction with the rest of the universe. It's one of the reasons why you have to keep the the atoms relatively small, because it can the more atoms that you add to a a quantum, the more qubits, right, which are individual atoms or particles in a quantum machine. The more you add, the more likely it's going to interact with the rest of the universe somehow, accidentally.
Mhm.
Beyond the engineering that you contain it with.
Yeah, I
And
don't know if those lava tubes, going down one of those lava tubes and having one down there would solve that problem, the gamma rays and all of that.
well, there's a lot of trial and error, I imagine, but um, but it's kind of like logical deduction and figuring it out as you go. Um, but we do know that the atmosphere protects us from some, and we know that Earth protects us from some. We know that some types of metal protects us from some. And if you add that together with the lowering of the temperature, and then try it out with a very small a group of quantum bits, individual atoms, and picking the substrate for the computer too, is probably a factor as well. Um, then you this is why it's something we haven't figured out 100 years ago, right? This is all. It's not new. We've had quantum computers for a while, but we haven't had good ones, right? We're just getting to the point where they actually work and do something useful.
And let's talk
Just in
about
the last 5 years.
yeah, let's talk about that. So the the near reported record of the number of qubits, I see IBM is reporting something like an 11,000 or sorry 1100 qubit chip, and different researchers are claiming a 6,000 physical qubit um, system. And so is that 1,000 qubit lot from IBM, is that a logical number of qubits? Are we actually expecting to get to hundreds of thousands to millions of qubits in the next 5 years, or are those results not really showing up, or is the industry being dominated by AI money and getting strangled in its infancy?
I mean, I, I I can tell you my perspective, the most of the noise comes from an AI, right, I think right now, but at least for me, um, I, I I have toes dipped into the quantum stuff, but it's mostly just it's not current state of the art engineering related stuff that I've been interested in. It's more fundamentals, and just in learning the physics of it. But
Right.
but that's something they've been teaching in school for. I mean, I remember quantum networking in school 25 years ago. And so they've been teaching that and doing that kind of work for a long time, long time.
Mhm.
Um, but but I don't know. The last time I was looking at quantum computers online and trying to understand the algorithms and stuff like that, which wasn't that long ago. It was maybe 3 or 4 years ago, I guess, where I was trying to be a little active in it. They only had like 100 plus qubits, or maybe not even that. It was relatively small compared to what you're saying. You're saying 1,000 plus qubits.
Yeah.
Um, that to me is mind blowing because each qubit is exponential in power. And I, it, are you aware of the current state of like publicly available qubits?
I believe that some of the more reliable results are still less than 50 logical qubits, even at the scale of thousands of physical qubits. Uh,
Break it.
the 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 ones that seem to be reliable are it's still saying 50 to 100 is the general industry target. And it may be sort of my speculation that the industry is not getting a lot of press, either from lack of results or over hyper focus on different technologies right now, because we're
Yeah.
seeing so much focus in AI compared to
Could
quantum.
yeah, Carl, could you put that more in layman's terms?
Well, let's talk about this. A qubit is a probability of a single state being zero or one, or left or right. And so when we're talking about a practical application, like figuring out what cities to visit. This is something that has thousands to millions of dependent variables. We can solve a what's called the traveling salesman problem
Which
in
is,
time. It's the class of optimizations. When you're talking about a traveling salesman, you imagine them figuring out the optimal route between cities in order to visit every city and minimize their travel cost. We could call this the FedEx problem or the UPS problem, where the UPS driver has a series of packages and they want to optimize the their fuel cost and how many left turns they have to make, etc. And so there are variables um, to that problem, and that is the distances between each of their stops. And so they have to calculate, well, what order do I take these stops in to optimize my travel time, to minimize my costs in fuel and time? And so it could be one to three to four, five, maybe variables comparing different arrangements of stops. And so if you're talking about conventional computers and GPUs, you will get to a system of thousands, hundreds of thousands of stops using a conventional computer or a GPU array. And quantum computing only really becomes interesting when you are able to beat a conventional computer. So that is getting that qubit count higher. There are some problems. Let's talk about cryptography or old school cryptography where you might be able to break that system using a smaller number of qubits. Like if you get to 1,000 qubits, the encryption we used online up until the the year 2010 could have been at risk, and that is the public key cryptography. Since then, of course, we have moved on to different post quantum algorithms, and those post quantum algorithms are invented in order to defeat the efficiency gains of quantum computing. And so it means that our public encryption infrastructure will not be vulnerable once the number of qubits gets past the logical qubits gets past about 1,000 to 2 to 4,000. Those are the practical sizes of the quantum computer, and so that is 100 times bigger than what we are actually achieving. And I think Mark's right when he says it is exponentially more difficult to get to each to get to linear progress in qubits. It's exponentially more difficult because it decoheres, error goes up, you need more error correction per qubit. So that's more physical qubits per logical qubit, and so yeah, that's a big question, and this is another thing to throw into the mess of, do you try it in orbit, or do you just get so much radiation that you're peppered with it from all sides, and the size and the timing of your operations go out the window then? So I hope that gives some layman's context as best as I can
yeah,
explain
a
it.
little better, a little better.
Well, I guess the next question that we can talk about is, um, do we think there is a world where a single corporation or a single superpower runs away with all of the quantum computing power in the world, in the globe? Do we see a future where America or China or IBM or Google cracks the problem and immediately solves problems that no one else can solve? what does that mean for our future?
So if you want my intuition, I think China's probably got far more infrastructure and longer lived infrastructure than we've had for a very long time, and I think we're trying to make that shift happen, but it's been that way for decades. And I mean, I keep reading about reports about how they have completely automated systems with humanoid robots and all that. So I don't know how true any of that is because you can't really. Um, I mean, unless you're trying to connect the papers together and look at the economics that are available in with high fidelity, is it's sometimes just noise, but reasonably, that's been kind of my concern that they're probably already there. So, in that in some ways, maybe not in all ways, but infrastructure wise, I think they at least have that capacity.
And it's astonishing to see the amount that China has improved in terms of their clean energy technology, both renewables and especially nuclear. Um, if they were more transparent, of course, and we have Jason Chow who's commented on this, is that we don't understand the regulatory environment in China. We don't see the transparency the same way that we have in America, and we don't see the same risk profile because there's less transparency and accountability in that system. And so, if there is um, a big advantage, we may not know the cost to human thriving and human life for many years.
I mean,
So, go ahead.
yeah, I don't really know what to say. I kind of to some degree I kind of like I have this envy of wanting to explore China untethered, just just to see what's really going on. But I mean that's not really a possibility. So the best thing we can do is just focus on our current state of things. Which I mean we excel at innovation. I think
Mhm.
in creating these new technologies. What China is good at is copying, and not really coming up with original ideas, but definitely running loose with established ideas. Although there might be some fringe. I mean, it's not like they're uh, a complete nation of non-innovators. They do have some innovators there, but as a general um, group, that's not their they're not winning the Nobel Prize every year. So, but that's just their, and I don't think that's politics. I think that's just the way they're set up and and the way their innovation engine uh, is established. Which quite honestly, the way we're set up here in the U.S., we do we do reward innovation. Maybe not ideally, but probably better than the rest because of our market system.
All right.
So
Okay.
Yeah, yeah, I want to back up. I want to back up a little bit. Um, the problem of getting to absolute zero, is that the biggest problem with quantum computing progress right now? And how much money is saved, let's say, possibly other things being equal by doing this on the moon?
it's a matter of scaling it. So we can do it with relatively low qubits because the engineering requirements are less. But as soon as we start scaling it to larger qubits to make them more viable for larger, longer run applications, algorithm applications, it becomes more complicated. So it's just a matter of, and it really is. I mean, there's a lot of factors, right? You can make more efficient algorithms to make it so that it doesn't require so much time. You can make it so that I mean, colder is better too, Okay, but I mean, once you get to absolute zero, then really the only issue is still radiation issues, which also collapses the qubits. It basically stops the function from working, right? It stops the system from working, and then so that becomes something that's very difficult to predict, except for just lots of shielding, and that's really all there is to it. It's making sure that nothing from the environment, from the rest of the universe, and I literally mean the entire universe is radiating everywhere and causing and could potentially cause a random reaction with one of the qubits, any one of the qubits, to cause interference, right? To collapse the system, and and that will stop the algorithm early and prevent your outcome, right? Prevent your results, and so that's the engineering problem. And so if you and while space might sound good as from the perspective of cooling, it's not ideal for from the perspective of radiation protection. So if we
We,
want if we want to go there, for whatever reason, it would have to be better than Earth, right? Or we just run out of space somehow, right? So, and from my perspective on the radiation issue, I don't see it as being better from Earth, in part because any company can, without space infrastructure, can build a quantum computer, okay, with minimum funding. Um, I mean, you need funding for the computer, but you don't need funding for space, and then you don't have to do any type of R&D for extra shielding too, and that's a big unknown, right? We like nobody, somebody would have to have a reason to do it, like a reason to put it in space, theorizing that it had some sort of advantage, and then actually do the research, um, and maybe somebody like Elon's doing that because he's got the space infrastructure, but and maybe he's experimented, who knows? But I pretty much guarantee that if he's doing that kind of stuff, he'd be bragging about it. He wouldn't be. He doesn't brag about his failures, but he brags about the stuff that he does well, and he doesn't really brag too much about quantum anything. So it's
it's too early to tell if it's advantageous is really the bottom line, right?
what's that?
Is it too
So
early?
the bottom line is whether it's advantageous on the moon or not is we just don't know. It's too early to tell.
It's too early. There would have to be a situation where it's like really easy to set up a quantum computer in space or on the moon, and the infrastructure's not there, and the drive isn't there, and it's like theoretically from this perspective, it's like it probably won't. It's probably no better than Earth or worse. So as far as engineering goes, and then the cost factor of the logistics alone just makes it really hard. So it's not like theoretically it's not impossible. It's just probably it's harder than creating a quantum computer on Earth, and we're probably decades out from making
Obviously,
that
yeah,
something viable. Yeah.
yeah. It would preclude that we'd be there and we'd really have a lot of infrastructure and we'd be pretty advanced into the colonization of the moon.
Now, if it were just about the cooling, I would say that it'd probably make a lot of sense. Like, but it's not. So that's like the core issue, I think, for me.
Yeah. Okay.
Well, we are unfortunately near the end of our abbreviated segment here. So thank you, Mark Havens. I guess the last is, what are your final thoughts on the future of the world with quantum computing? And if you want to tell us about your upcoming projects, anything you've got going on.
Um, what is going on with I? I've always been very optimistic about quantum stuff, but there's so much unknown. I I really look forward to seeing AI transcend into quantum types of states, into a quantum environment. That's probably going to be a game changer. And the more work I do with that, the more I'm thinking that it probably will require a lot fewer algorithms than AI, because some of the work I do um, does not require neurons for AI. I have a system right now, a paper um, that uses a neuron less AI system. Right? It's oscillator based. It's not neuron based. So seeing something like that emerge in a quantum algorithm might be very very sexy for me to look at. I'm looking forward to something like that emerge. Um, but as far as future projects for me, I am trying to focus on uh, how we can survive a collapse of meaning in life outside of work. So trying to if you follow my feed at all, I focus a lot on pre-civilization types of meaning and purpose, because I see civilization as something that's kind of drained humanity um, from from having independent, uh, sovereign type of meaning, and that's sort of my research right now, exploring humanity and self, and understanding understanding what we really are, so that once the machines replace us with replace our need to work, we'll still have somewhere to go as humans. So that's what I'm doing
Right.
right now.
All right. Thank you, everyone, for your contributions. This has been the Ecomodernist channel live. You can find us here on YouTube at Ecomodernist1 or Ecomodernist channel live. You can find us on Facebook at the Ecomodernist Society of North America, and find us online at esna.earth. Don't forget, you can support us on Patreon. Look for the Ecomodernist channel at patreon.com. I'm Carl Pauls. You can find us rebroadcast to my various social medias, LinkedIn, Twitter. I'm Carl Alex Pauls, and various other places like on Twitch at Soyaddle or soyaddle.tv, and on Kick at Soyaddle. So thank you for all of your contributions. Again, remember, emissions first, peace and justice